Um, Welcome back. Please kindly subscribe to our channel by clicking on the subscribe button below and also the bell icon so as to be getting update. Okay, in today's class we're going to continue from where we stopped during the last class. The topic we're going to be looking at for today is number 1. We have rates law, which is also known as rates equation. Number 2, we have law of reaction. Number 3, we have integrated rates law. Also, you have fractional life. Now, you may want to ask, what's the difference between fractional life? Half is also a fraction, so this fractional life actually account for every other fraction apart from half. Okay, so we have, for example, 1/3, that's 1/3. You may be asked to solve for the 1/3 time, or the 1/4 and the rest of them. So all those one falls under fractional life. Then we have effect of temperature. On rate of reaction. Okay, so these are the 5 topics we are going to look at in this episode of this video. Okay, we're going to start with the first one, rate law, which is also known as rate equation. Okay, now what is rate law? Rate law is also known as rate equation. So just in case some person might want to use rate law, while some other persons might want to use rate equation. It is simply an equation that relates the rate of a chemical reaction to the concentration of the reactant. I repeat, it is an equation that relates rate of a chemical reaction to the concentration of the reactant. Now, if you could recall, one of the factors that affects rate of reaction is concentration. Okay, we know very well that increase in concentration brings about increase in collision frequency, which in turn is going to give rise to increase in the rate of the reaction. Okay, so an equation that shows this relationship, how concentration varies with rate of reaction, is what we call the rate law. Okay, so I will say rate law is an equation that relates the rate of a reaction to the concentration of the reactant. Now let's take, for example, we have a reaction that has, let's take a reaction that has just one reactant. We have A given us C. Now if you look at this is a reaction A giving rise to C. This small letter A is the stoichiometric coefficient of this A. The small letter C is the stoichiometric coefficient of this C. Now this R is what is separating the reactant from the product. Reactant is always at the left hand side of this arrow, while the product is always at the right hand side of this arrow. Okay, so in this case now the reactant is A. So rate law is going to be my rate, which is symbolized by R, is equals to K, that is rate constant, into concentration of A. Now this square bracket stands for concentration. Now this will be raised to the power of X. Please take note that this X, that this concentration of A is raised to, is not the stoichiometric coefficient. Instead, this X is what we call the order of reaction. Okay, so we have my R is rate of reaction. This becomes concentration of A, where X becomes order of reaction with respect to A. Now this X is order of reaction with respect to A. Alright, and since it's order of reaction with respect to this A, okay, this can also be, the X can also be equals to the overall order of the reaction. Okay, so what if in a case whereby we have a reaction that has two reactants? Let's say, for example, we have A plus B giving us C. Now this reaction has two reactants. Okay, so our rate law for this will be R equals to K, concentration of A raised to the power of X, times B, concentration of times concentration of B raised to the power of Y. Now our X is order of reaction with respect to A. Our Y is order of reaction respect to B. Okay, so for us to get the overall order of the reaction, so therefore overall order of the reaction is going to be equals to X plus Y. Now overall order of the reaction is always to sum up the orders of reaction in a case where we have more than one order. So in this case now we have X and Y. X is the order of reaction with respect to A, Y is the order of reaction with respect to B. So when you add both of them together, you have the overall order of the reaction. Okay, now in the previous illustration I made, I used a reaction that had just one reactant, and of course we have just one power, so there is nothing to sum up here. So the only power here, which is X, we can say the X is order of reaction with respect to A, which also doubles as the overall order of the reaction, or simply put, the order of the reaction. Okay, since we are done with this now, let's look at the various orders of reaction. Okay, so we have orders of reaction. Okay, so we have various orders of reaction. We have zero order reaction. We have okay, so we have zero order reaction, we have first order, we have second order, and so on and so forth. So we're going to start off with the first one. Let's start off with the first one, zero order reaction. Now, it is important for us to know that the reaction is said to be zero order if the sum of the power in the concentration term in the rate law is equal to 0. Now, let's take, for example, let me take that again. A reaction is said to be zero order reaction if the sum of the exponential term in the rate law is equal to 0. Do not forget that those exponential terms are the orders of the reaction. Okay, so if, for instance, the previous one we had x plus y, if x plus y is equals to 0, that reaction belongs to zero order reaction. So let's start up with for a reaction that has just one reactant. We say, for example, if I have A giving me C, now my rate law becomes this, a reciprocal of x. Okay, if x equals to 0, so therefore we're going to have a zero order reaction. Now what do I mean? Let me erase off this. If I say R equals to K X, and this becomes K equals to 0. Anything raised to the power of 0 is 1, so this becomes K. So therefore, for a zero order reaction, R is equals to K. Now if we take a look at this, for a zero order reaction, the rate is independent of the concentration. Okay, remember rate law is basically an equation that relates the rate of a chemical reaction to the concentration of the reactant. Okay, so in this case now, this rate law is R equals to K into concentration of A raised to the power of X. Now, if X equals to 0, everything here will be equals to 1. 1 times K is K. So you realize that for a zero order reaction, note, for a zero order reaction, the rate of reaction is independent of the concentration of the reactants. Okay, so it's what if we decide to derive the zero order reaction for reaction that has two reactants. Now this is it. If I have, let's say, for a reaction this becomes R equals to K. Now we have two reactants here. The first reactant is A and the second reactant is B. Okay, unlike the first one where we had just one reactant, A. So in this case now we have two reactants, A and B. So in this case now, for this reaction to be a zero order reaction, the sum of the power, if x plus y is equals to 0, that will be a zero order reaction. Now this takes us back to what I told us earlier. For a reaction to be a zero order reaction, the sum of the powers on the concentration term in the rate law must be equal to 0, right? So if you look at this x and y, if you add up both of these two powers, which is order of reaction, and it gives us 0, of course that means that reaction is a zero order reaction. Okay, so please take note of this point I just made here. That means take note of this point. This point is very, very important. Okay, so let's look at first order reaction. Let's look at first order reaction. Now I want to divide this. Let's say let's use first a reaction that had just one single reactant. For this reaction, for A, okay, now my rate law is R equals to K. Now for first order reaction, okay, let's take it this way. Instead of saying that, we say if x equals to 1, the reaction is a first order. Okay, so we say, so therefore R equals to K. Alright, for first order reaction, x will be equals to 1. So anywhere you see x, you put your 1, so this becomes R equals to K. And of course, anytime you have 1, you can always ignore writing it. Alright, so we have this. R equals to K times the concentration of this. Okay, what if in a case whereby we have a reaction that has two reactants? We say, what if I have A I have this. Say for a first order reaction, x plus y, sum of the powers must be equals to 1. Okay, now this can be obtained by saying x equals to 0, y equals to 1, or x equals to 1, y equals to 0. Anyhow you want to do it such that when you add up both of them, it will give a value of 1. Do it. So for a reaction that have two reactants, so that's the rate law. So they can give you a reaction that has 3 reactants. All right, they can give you one that have 3 reactants, and then you're asked to write the rate law. Okay, so first, rate law is written for just reactant, not the product. Okay, so you notice that if you do that here, so that because anyhow you want to do, you can say this becomes R equals to K into A, X will be 0, B, Y will be 1. So this becomes R into K, because A, anything raised to the power of 0 will be 1. Alright, so basically that's how we write rate law for the first order. Now for a second order reaction, we have okay, let's say now my rate right now for a second order reaction where X, for a second order reaction, this power will be equals to 2. That's the order the order of the reaction. So this now becomes, so therefore R becomes equals to K. If you notice the rate law for zero order reaction, the rate was independent of the concentration of the reactant. Right now for first order reaction, the rate is dependent. That means if you increase the concentration of A, the rate of the reaction will also increase. For a second order reaction, the rate is also dependent. This time around, if you increase the concentration of A, the rate will be times 2, because the concentration of A is raised to the power of 2. Okay, so this is the rate law for a reaction that have just single reactants. What if you have the one that have 2 reactants? For example, we have A plus B giving us C. So the rate here becomes equals to X Y. Okay, now for a second order reaction where X plus Y is equals to 2. Now what are the possibilities here? You can have X to be equals to 1, Y to be equals to 1, or vice versa, or X equals to 0, Y equals to 2, or X equals to 2, Y equals to 0. Now these are the 3 possible options that could result from here. At the end of the day, the sum of the power must give us 2. So whether it is 1 plus 1 or 2 plus 0, as the case may be, it doesn't really matter. Okay, so that is that for the rate law showing order of reaction. Okay, all right, so okay, we're going to be talking about unit of rate constants. Now if you could recall, in the previous video or the previous session, I actually told us that the K in the rate law is rate constant, and rate constant unit varies for the various orders of reaction. So here we have a general formula that will help us to quickly remember the units of various orders, the units of rate constant for various orders of reaction. This is K equals to mole per liter, close bracket, 1 minus N per second. Please do not forget that this N here is the order of the reaction, and it's very important to know that This can be written also as molar 1 minus n per second. Why? Because this capital letter M stands for molar, is the same thing as mole per liter. Alright, so most of the times they will not, or they wouldn't write mole per liter as the unit. It might just be something like capital letter M. This stands for molar, and molar is mole per liter. Okay, now let's start with for second order reaction. Now for second order reaction, N would be equals to 2. Okay, N will be equals to 2. So if you come here, anyway you see N, you insert 2 here. So we have 1 minus N, 1 minus 2 per second. Then 1 minus 2 is minus 1. So minus 1, expanding this bracket, we're going to have this. Okay, so this is the unit of rate constant for a second order reaction. What if I decide to use molar in place of that? What if I decide to use molar? Let's say I have if I come here and I'll say K, instead of using mole per liter, I'll use capital letter M, 1 minus N raised to the power of 1. Okay, and we know that this is going to be 1 minus 2, and this becomes M minus 1. Simple. So if I'm using molar, which stands for mole per liter, the unit is going to be per molar per second. Okay, that is that for a second order reaction. Let's look at that of a first order reaction as well, before we finally move down to that of a zero order reaction. So we'll say for first order reaction, the N here will be equals to 1. Do not forget that this N is the order of the reaction. This N here is the order of the reaction. Don't forget that, please. This N here is order of reaction. Okay, so this becomes K (1 minus 1). Now 1 minus 1 is 0, so this becomes 0 per second, which becomes per second. So the unit of rate constant for first order reaction is per second. Please, it's important I state this, that there are some cases whereby they will not give you the time in terms of seconds in the rate constant unit. What if they had given us per minute, per hour? Minute, of course, is also a unit of time. Hour is also a unit of time, but the SI unit of time is seconds. What if in a case whereby they give us in minute or hour? Okay, you have to work with it like that, except the options had answers in another unit. But other than that, if the rate constant has per minute, per hour, it can still be regarded as first order and can still be used like that. Okay, so let's look at for zero order. We say for a zero order reaction, our N here becomes equals to 0. So we have K anywhere I see N, I'll put 0. So this becomes of course, anything. So this becomes, okay, let's come here. 1 minus 0 is 1, so see the same thing. So this now becomes so for zero order reaction, the unit of the rate constant is this. Okay, so that is that for unit of rate constant. Now let's look at integrated rate law / rate equation, as well as the half-life of various orders of reaction. Now, what is the importance of this particular topic here? Okay, this topic is important because we're going to be using it to carry out calculations for each order of reaction. Okay, now shortly we're going to see the importance of each of these guys. Now, for zero order reaction, zero order has integrated rate law, right? First order has also integrated rate law. Second order also have integrated rate law. All these orders of reaction, the integrated rate law has 4 parameters or 4 variables: initial concentration, final concentration, time, and rate constant. Right? Rate constant for zero order reaction has a unit that is different from rate constant of a first order as well as a second order. That was why it was important for us to know how the units for various orders of reaction look like. Okay, so if you look at this particular one here, for a zero order reaction, the rate law for a zero order reaction is A0 equals to AT plus KT. Now, what is A0, if I may ask? A0 is initial concentration of the reactant. AT is the final concentration of the reactant. T is a time. K is its rate constant for zero order reaction, because this is equation for zero order reaction. It simply means that you may be given 3 among these 4 variables here, and you're asked to solve for the remaining one. Remember, we have 4 parameters here. They will always give you 3 parameters, and you're asked and you're to solve for the other parameter. Okay, so we're going to look at for first order, second order, and then afterwards we're going to solve we're going to start solving question. Now, it is also important we discuss half-life as well, because half-life will also have different formulas for of half-life for the various orders of reaction. Now, first, what is half-life? As the name implies, half. Now, there are so many definitions to half-life, but I'm just going to give us the ones that will easily stick to our head or our brains. Now, half-life is a time it will take for half of the initial concentration of the reactant to react. I take it again. It is the time it will take half of the initial concentration of a reactant to react, or you can simply say it is the time required for 50% of a reactant to react. Of course, 50% is half of 100%. Now, in a layman understanding, let's assume, for instance, you want to start up a reaction. Of course, if you're starting up a reaction, you must start up with a reactant, because reactant is what will convert to a product. So let's say we actually started off with 10 mole per liter concentration of the reactant. Half of 10 is 5. So the time it will take that reactant to reduce to 5, or the time it will take 5 out of that 10 to react, is what we refer to as a half-life of that particular reactant. So half-life simply means the time it will take half of the concentration of a reactant to react. Okay, so having said that, we're going to look at the formula for zero order half-life, because every order of reaction have their various formulas for half-life. So for zero order half-life, we have T half is equals to A0, initial concentration of the reactant, all over 2K, where K is a zero order rate constant. A naught is the initial concentration. Okay, now for first order, if you look at this, we have this, the integrated form of a first order reaction is actually written here. We have log AT, where AT is the final concentration, A naught is the initial concentration, minus KT all over 2.303. Okay, so this is a formula for integrated rate law of a first order reaction. They might give us 3 out of these 4 parameters, and you're asked to solve for the other one. Of course, 2.303 is a constant. As long as you're using log, you must attach this 2.303. Some other formulas might decide not to attach log here. If you remove this log here, you must remove this 2.303. Okay, now for first order reaction, what is the half-life formula of a first order reaction? We have T half equals to 0.693 all over K. Now remember we said the various orders of reaction, they have different formula for their half-life. So for this T half, we have 0.693 all over K. Okay, now it is important for us, if you look at this formula very well, you notice that the half-life formula of a first order reaction do not in any way contain concentration of the reactant. So I can simply say that half-life of a first order reaction is independent. Half-life of a first order reaction. Half-life of a first order reaction. Let me write that again. Okay, so we say that half-life of first order reaction is independent of the initial concentration of the reactant. Do not forget that when we actually discussed Rate's law for a zero order reaction, we said that the Rate's law of a zero order reaction is R equals to K in brackets concentration of A raised to the power of X, where X equals to 0. And I went ahead to say that for a zero order reaction, the rate of a zero order reaction is independent of the concentration of the reactant. If you could recall, in this video I said that. Now why is it so? Because if you look at the zero order rate equation, the concentration term is raised to 0, and anything raised to the power of 0 is 1, and as such, concentration will be raised to the power of 0, which will give us 1. So for a zero order reaction, the rate is independent of the initial concentration of the reactant. Do not confuse or mix it up with that of a first order reaction, where half-life, for first order reaction, the half-life is what is independent of the initial concentration of the reactant. For a zero order reaction, it is a rate that is independent. Okay, all right, now let's look at second order reaction. Just like we have here, the integrated rate law, rate equation, we have 1 over AT equals 1 over A naught plus 1 over KT. Of course, we already know what AT is: final concentration, initial rate constant, and time. Now if you notice, all the integrated rates law all have same parameters. The only difference is just the way the parameters are being related to each other. They all have initial concentration, final concentration, time, and rate constant, which of course they'll always give us 3 and you'll be asked to find for 1. Now half-life of a second order reaction is T half equals to 1 over K A naught. Okay, so that is that. So the next thing we're going to do now is that we're going to solve problem examples, right, ranging from 0 order, first order, second order, at least so that we understand vividly what we've actually done so far. Okay,